6.2 one-to-one functions and inverse functions. Determine whether a function is one-to-one. A one-to-one function, each x in the domain has one and only one image in the range, meaning 1x to 1y and vice versa. So we're going to determine which figure represents a one-to-one function. So only one x goes to one y goes to one x. So these are our x's, it's always on your left side, and the right side is y. So you see how these two go to 1y, these three go to 1y. This is not one-to-one. It's not one-to-one because the x's are sharing y's. You're not allowed to share at all for one-to-one. If we look at the second one, right, those are our x's, these are our y's. Everything goes one-to-one. One x to one y, one state to one population. So yes, this is one-to-one. You can determine one-to-one functions using the horizontal line test. If every horizontal line intersects the graph of the function in at most one point, then the function is one-to-one. Okay, so this is not one-to-one. This graph right here, you see how it hits twice using the horizontal line test? It is not one-to-one. So we're going to use the horizontal line test to determine whether the function is one-to-one. So this is the horizontal line test. We use horizontal lines. And you see how it hits twice, right here, right here, right here, right here. It hits twice the entire time. Because this point, that point, let's say it's, let's just say it's 1, 3. So that means this point is negative 1, or positive 3. So you see how they share the y? So this is not one-to-one. Now, our next graph, it is one-to-one. It's hard to see. This part right here, it actually goes like that. It's not a flat line. It curves. So if we did the horizontal line test, it is one-to-one. Determine the inverse of a function defined by a map of or a set of ordered pairs. So find the inverse of the function defined by a set of ordered pairs. Then we're also going to find the domain and range. So inverse, that's a new word. Inverse. What that means to us, it means opposite, right? When you think of like what's the inverse of something, you're thinking of the opposite. So it means opposite. In math, it means switch x and y. And in inverse, it's notated with that little symbol right there, f to the negative 1. That's notated. That's notation for inverse. So let's go ahead and find the inverse. So the inverse, we're just going to switch all of our x's and all of our y's. So all of our x's will be switched with the y's. So we have negative 27, negative 3. Only the number changes, only the position. The value and the number, it stays the same. So then we have negative 8, negative 2, negative 1, negative 1. I switch those, you just can't see it. 0, 0, same thing, I switched those, you just can't see it. 1, 1, I switched it. 8, 2, and 27, 3. That is our new inverse function. Now, is this one-to-one? Yes, it is one-to-one. So, is it one-to-one? Yes, it is one-to-one because 1x, 1y, nothing repeats. No numbers repeat. No x's repeat. No y's repeat. So let's go ahead and state the domain and range. So the domain of the inverse, that's all of our x's, our new x's. So it becomes negative 27, negative 8, negative 1, 0, 1, 8, 27. Our range of the inverse is all of the y's, are all of the y's now. So -3, -2, -1, 0, 1, 2, 3. The graph of a one-to-one function f and the graph of its inverse function are symmetric with respect to the line y equals x. I'm going to explain that later in an example. All right, example 4. Consider the function f of x equals 9x minus 4 and g of x equals 1/9 x plus 4. Find f of g of x, find g of f of x, and determine whether the function f and g are inverses of each other. So f of g of x, all that means is f composed with g. That's all that means. You see how we're tying it back to 6.1 now? And then for b, g of f of x, that's the same thing as g composed with f. So let's do f composed with g. So we have our f function. It equals 9x minus 4, and then we have our g function. All right, so remember, second into first. So second into first. So we have 9 blank minus 4, and in that blank, we're doing 1/9 x plus 4. Okay, so in between right here, you see how there's no plus or minus right there? If there's no plus or minus right there, we're allowed to cancel out those 9s. So what we're left with is x plus 4 minus 4, which is just x. So f of g of x equals x. All right, let's do part B. So part B, we need to do g of f of x, or g composed with f. So our g function, that's 1/9 x plus 4. Our f function is 9x minus 4, so second into first. So second into first. So let's do that. We have 1/9, sorry, wrong color. We have 1/9 blank plus 4, and in that blank, we're putting 9x minus 4. All right, so we can get rid of the pink parentheses in the middle, so we have 1/9 times 9x minus 4 plus 4. The 4's cancel, so we're left with 1/9 times 9x. We can cancel those 9's out. So all we're left with is x. So g of f of x equals x. Do you notice how they both equal x, right? That leads us to part C. Determine whether the functions f and g are inverses of each other. They are inverses. I'll tell you why. So they are inverses. When f of g of x equals x and g of f of x equals x, it proves that the two functions are inverses. Doing f of g of x and g of f of x is how you check inverses. So if you're ever asked, check the inverse, you do part A and part B. I will let you know for this class you do not need to check. You don't check for this class. But when you go to pre-calculus, you are going to need to start checking. But for college algebra, you do not need to check. Alright, let's find the inverse function defined by an equation. So our step 1 is in at y equals f of x, interchange the variables x and y to obtain x equals f of y. Step 2, this equation defines the inverse function implicitly. If possible, solve the implicit equation for y in terms of x to obtain the explicit form. Check the results by showing that the inverse of f of x equals x and f of the inverse equals x. So, what does all that mean? Switch x and y, that's step 1. Step 2, solve for y. Step 3, which you're not going to need to do, we're still going to do it, we're still going to practice with this example, but all step 3 is check. So to check, we're going to do the inverse composed with the function, that's this part, and we need to make sure it equals x, and then our second part is to do the function composed with the inverse and make sure it equals x. So we are going to check it for example 5, but you do not need to check for the test or for the homework. We're just doing it for this example. Alright, we're also going to talk about the domain finally. So we're going to talk about the domain. It makes more sense in example 6. Alright, let's find the inverse. F of x equals 2x plus 3 and check your answer. So first thing we need to do is change it to y. So we have y equals 2x plus 3. Alright, our first step is to switch x and y. So we'll have x equals 2y plus 3. So everything that's an x becomes a y, and everything that's a y becomes an x. Now our our second step is to solve for y. So let's solve for y. To solve for y, I'm going to subtract 3 to both sides. So we have x minus 3 equals 2y, divide by 2. So we have x minus 3 over 2 equals y. The last thing we have to do is just put it in our notation, and we have our inverse. Now we have to check it. So our third step. Alright, so we have to do 2 things to check it. Our first thing is to form the composite for the inverse. So we're going to plug function into inverse. So our inverse is x minus 3 over 2. Our function is y equals 2x plus 3. So we're going to plug second into first. So let's do that. So we have blank minus 3 over 2, and the blank we're plugging in is 2x plus 3. So we can get rid of those 3's. We're left with 2x over 2, which is just x. So that works. Now we have to check the other way around. We have to flip it and see if it works. So our second step is to do the function composed with the inverse. So we have our function, it's y equals 2x plus 3. We have our inverse, it equals x minus 3 over 2, so second into first. So second into first wherever there's an x. So we have 2 blank plus 3, and the blank we're plugging in x minus 3 over 2. In between here, since there's no plus or minus, we can cancel out the 2's. So we're left with x minus 3 plus 3, which is just x. So they both work. So you checked it. It's great. You're all good. So they are inverses of each other. Because in pre-calc, you can find an equation that you think is the inverse, but it doesn't actually work out. Not every equation has an inverse. Alright, now we have to find the domain and range. So we have to find the domain of the function, the range of the function, and then we have to find the domain of the inverse, and then we have to find the range of the inverse. Alright, so I'm going to rewrite our function and our inverse. So our function is 2x plus 3, and our inverse is x minus 3 over 2. So let's start with finding the domain of each. So the domain of the function is all real numbers because there's no fractions or radicals. So the domain of the function is all real numbers. The domain of the inverse is also all real numbers. Yes, we do have a fraction, but there's no variable in the denominator. So the domain of the inverse is also negative infinity to positive infinity. And since we know inverse is just opposite, the range of the inverse is negative infinity, and the range of the function is negative infinity, positive infinity. That's not a good example because everything's infinity, but that's how we find them. We just switch them. The next example is a perfect example on how to find the domain with an inverse. Alright, it's 1 to 1. Let's find the inverse. We are not going to check it, so don't even worry about that. We're not checking this, but we are going to find that domain. So we are going to find that domain and range. Alright, so first, let's change that to y equals. So we have y equals 2x plus 1 over x minus 1. Now we're going to switch every x to y and every y to x. So we have x equals 2y plus 1 over y minus 1. Now we need to solve for y. So regardless, I'm always going to multiply by that denominator because there's something I want in there. Since there's something I want, I'm going to multiply by the denominator to both sides. So I'm going to distribute the x. That means we have xy minus x equals 2y plus 1. Let's keep solving for y. So I want y by itself. That means everything with a y should be on one side and everything without a y should be on the other side. So I'm going to add x to both sides. And when we do, we have xy equals 2y plus 1 plus x. I'm going to subtract 2y to both sides because it has a y, so I want it on the left. So when we do that, we have xy minus 2y equals 1 plus x. Now they both share a y, so I'm going to take it out. And when we do, we're left with x minus 2 equals 1 plus x. I'm going to bring this up here. So we're going to, just going to rewrite it. We're going to divide by x minus 2 because it gives us y by itself. So we have y equals 1 plus x. It could also be x plus 1 over x minus 2. So we just change it to notation. And there's our inverse. So we're not going to check this, but let's go ahead and find domain and range. So on the homework, on the test, you do not have to check. So we need to find the domain of the function. We need to find the range of the function. Then we need to find the domain of the inverse. And then we need to find the range of the inverse. Alright, so I'm going to rewrite our functions. Our f represents 2x plus 1 over x minus 1. Our inverse represents x plus 1 over x minus 2. So the domain of the function, its bottom can't be 0, so x minus 1 can't be 0. That means x cannot be 1. So let's find the domain of the inverse. So the inverse, we have x minus 2 cannot be 0, so x cannot be 2. So now, to find the opposite, we're just going to switch them. So the range represents y, so we say y cannot be 1. And then here, we change it, so the range is y, so then y cannot be 2. It's because they are direct opposites of each other. Because they're direct opposites of each other, that's why we just switch them. Alright, the graph of a one-to-one function is given. Draw the line of the inverse function. So I'm going to pull out the points for our function. We have -2, -2, 0, -1, 1, 0, 2, 1/2. So that's for the function. Now for the inverse, we know how to do that. We just switch the points. We switch x and we switch y. So we have -2, -2, -1, 0, 0, 1, and 1/2, 2. So let's plot those points. We have -2, -2, -1, 0, 0, 1, and 1/2, 2. Doesn't it look like the reflection, the mirror of that? Doesn't it look like if over this line, if you folded it, they go perfectly on top of each other? That's what I was saying before, that inverse functions that are graphed, if you fold it over y equals x, they will always go on top of each other. Because inverse means direct opposite, which means mirror image. Alright, example 8. The domain of a one-to-one function is 5 to infinity, and its range is -2 to infinity. State the domain and the range of the inverse. Alright, so we're given domain of the function. It's 5 to infinity, and we're given the range of the function. It's -2 to infinity. So now I need to find the domain of the inverse. And I need to find the range of the inverse. We do it the same exact way, we just switch them. So the domain of the function is the range of the inverse. So 5 to infinity. And then the range of the function is the domain of the inverse. So that would be -2 to infinity.